All right, welcome back everyone to section 4, the definite integral, using the nice fundamental theorem of calculus. The second topic that I want to bring up here in this section is this idea of total area, and this is versus or compared to the net area, which is something the definite integral gave to us. So we're interested in now something different, the total area. And to see why this is useful, I want you to consider the following problem. So Ryan throws a peach straight up into the air at t equals 0, and then he catches it, right, 6 seconds later. The peach's velocity during the time can be well approximated by this equation here, 30 minus 10t, where t is in seconds, and v of t is in meters per second. So I'd like to, first of all, just go ahead and evaluate out the definite integral from 0 to 6 using the fundamental theorem of calculus, and let's interpret the result. Okay, so the first thing, in order to use the fundamental theorem of calculus, I need to come up with an antiderivative. So if I go ahead and think of this v of t as some derivative thing, and I'll use capital V of t, no, let's use s, right? So s is going to be like a position is what you should think about this. So s is going to be equal to the antiderivative. So the antiderivative of 30 will be 30t, something that when I take the derivative of it, I get 10t. Well, it's got to have like a t squared in it, right? But then, let's see, I need a 10. If I took the derivative of this, I would just get a 2. So I'm going to go ahead and throw a 5 out in front. Now let's check. If I take the derivative of this, yes, the 2 comes down and I get the negative 10. Perfect. And then plus really any constant, right? But again, any antiderivative will work. So there's my position function right there. And so therefore, the definite integral from 0 to 6 of v of t is going to be equal to s of 6, this is the antiderivative, minus s of 0. And so the position at height 6, well, if I plug that in, let's see, I'm going to get 30 times 6, that's going to be 180, minus 5 times 6 squared, that's going to be 36, minus s of 0. So s of 0, if I plug in 0, I'd get 0 minus 5 0 squared, also 0. All right, so if I went ahead and multiplied, this would be 150 plus another 30, so that'd be 180. Oh, 180 minus 80 minus 0, so I'm going to get 0. And of course, if I interpret this, right, my units for v of t are meters per second, and my units for t are seconds, so I would multiply these together, and this would be 0 meters. So this answer gives me out 0 meters. And remember, this is the total change, right? The total change in this antiderivative function. This is a total change in the number of meters, right? So the displacement, you can kind of think, I take a peach, I throw it straight up, it comes back straight down, and then I catch it, right? How much has it really changed? Well, it is saying that it's been displaced 0 meters. That really hasn't changed, it hasn't moved at all, it hasn't been displaced. But in reality, it's moved quite a lot, right? Actually, I threw it up, it traveled a bunch, and then it came back down, right? So this is the difference between net area versus total area. Part B asks, what is the total distance traveled by the peach, right? So this is not just how much was it displaced, but how much total distance did it travel. And so the way that we can think about this is that for the first 3 seconds or so, it's going up, and then for the next 3 seconds, it's coming down, right? If we were to actually graph this velocity thing, maybe a little mini graph here, if we were to graph velocity, here's at 3, here's at 6, initially it's up here at 30, and then if you were to plug in t equals 3, right, you'd get 30 minus 30, that would be at 0. And then down here you would have at 6, it would be at negative 30. And again, kind of all of this negative area down here perfectly cancels with all of the negative area up here. So the displacement is 0, but it traveled a lot. And so the way that we try to figure out, how much did it actually travel is that we break this up into a couple pieces. And we're going to count, okay, even if you're traveling in this negative direction, even if you're traveling back down, we're going to count this as travel. We're going to count this as you're actually moving and you get distance, right? So in this case, we're going to count it all positively. And that's the big change between net area versus total area. So we're going to count it all positively. So in this case, you can see I would really want to break up my integral. I want to do from 0 to 3. This is when the velocity was 0 and it started turning around of my v of t. And then I'm going to add that from 3 to 6. Again, the definite integral of my velocity. Oops, not dx, dt. There we go. Okay, in that case, we're going to have the same antiderivative, s of t. So this is going to be s of 3 minus s of 0 plus s of 6 minus s of 3. And no matter what answers we get out, we're going to count it positively. So I'm going to go ahead and include some absolute values here, right? So no matter what we get, we're going to count it positively, right? Okay, and so technically if I'm going to put absolute values there, I should put absolute values here as well. Okay, so let's go ahead and now calculate this out. So s of 0 I already know is 0. Actually, s of 6 I already know, also 0. But s of 3, that's the only one that I really don't know. So s of 3, if I plug in 3, I would get out 90 minus 5 times 9. So that's going to be 90 minus 45. So that's going to be 45. And remember, my units are meters here, technically. So that travels 45 meters up. Initially, it was at a height of 0. And then it turns around, and it travels 45 meters down. And before, this positive 45 and this negative 45 canceled out with each other, right? But now we're counting them both positively, that you went 45 meters up, and then you went 45 meters down, and so altogether you traveled, the peach traveled actually 90 meters, right? So this is the total distance traveled. And likewise, if you were to look at it, because we do have this nice nifty sketch up here, we could look at it like this. We have width 3, we have height 30. So if we do 1/2 base times height, this would be 1/2 times 90, that would be 45. So that's 45 meters, right? And likewise down here, this is base width 3, the height would be negative 30. And so when you multiply it together here, you get 1/2 base times height. That would be negative 45. But remember, we want to count it all positively, right? So that's where we get the 45 plus 45, which should be 90 meters. So that's how much distance the peach actually traveled, kind of by just looking at time 0 and time 6. You're kind of undervaluing. Maybe the peach just stayed there the entire time. Well, no. In reality, I threw it up. It came back down. It had a very interesting journey. Right? So total distance actually, I mean, there's different reasons why you want to know about this. Okay, so then let me give you a little bit of a definition here. Like I promised, we were talking about total area. So total area between f of x and the x-axis, not net area, total area on the specified interval, is going to be the definite integral from a to b of the absolute value. Again, we're counting it positive. Even if it's negative, we're always going to count it positive, dx. This is going to give us the total area. Okay? So, in fact, this is one thing that our calculators can do pretty well. So let me go ahead and show you. If I was to do the same example here, pull out my calculator, and I'm going to do this f int. So let's do math. And I remember it's 9, and I'm going to do the function not just 30 minus 10t, right? But if I wanted the total distance traveled, I'm going to do the absolute value. So I'm going to do second, and under number we can get abs, right? So this is going to be 30 minus 10 times x, close the parentheses for the absolute value, integrate with respect to x, go from 0 to 6. Close parentheses, hit enter, thinks for a second, 90, right? So it can show you that the total distance traveled was 90. So this is a great formula that we can use. Actually still plug it into our calculator and get out results. Okay. In general, though, I mean, if we need to show our work, we need to use the fundamental theorem of calculus. It takes a little bit more, so I want to do a little more practice on finding total area here. So here's another example. Ryan skateboards extremely poorly. I'm not a good skateboarder at all. Back and forth along a street. So, left some, then right some, so on and so forth. His velocity is given by this graph below. T is in seconds, v of t is in feet per second. So no longer meters per second, feet per second. Okay. How far is Ryan from where he began 12 seconds later? So these are fancy words here, right, to say displacement. Which means that you want to calculate out the integral of this velocity graph from 0 to 12 dt. So this is not total distance traveled. This is not total area. This is net area, right? What was my displacement? How far am I from where I began? Okay, well this one we don't have an equation, we have a graph. So let's go ahead and start looking at this and try to calculate out the area. So I'm going to kind of break it up into some pieces here. This square right here, you have to be careful because if you're just staring at it, you would say, this has area 1, right? It has height 1, it has width 1, so 1 times 1, 1. But not actually, right? Look at my scale down here. They're trying to trick me. 0 to 2, right? So that's width 2. So this has width 2 and height 1, so this has area 2. Likewise, this triangle up here, width 2, height 1, so if I did 1/2 base times height, right, this is actually going to be 1. All right, likewise, width 2, height 2, so 1/2 base times height, this is going to be area 2. Remember, this is all getting counted positively, right? It's above the x-axis, or I guess the t-axis in this case. Now let's go over here. From 4 to like 9 or something like this. All right, this one's 4, this one's 9. From 4 to 9, it looks like it's below the x-axis, but this is just one big triangle, right? So the height of the triangle looks like it's -2, right? So the height is right here. And the width of the triangle, again, from 4 up to 9, right? So this is going to have width 5, so altogether 5. So if you did 1/2 base times height, 1/2 the base, 5, times the height, -2, this should be counted as -5 altogether. That's this entire piece. Let me maybe shade this in a little bit red here because it's counted below the x-axis. Okay, so you can see over here, in total, I traveled 5, right? I traveled 5, and then I came back 5, right? So I traveled in the forward direction, turned around, came back, probably where I started. And then let's finish this out here. This one is not a triangle, right? It has kind of a weird piece here. So I'm going to break it up. So, okay, this one has height 2 and width 1. So the overall area for this triangle will be 1/2 base times height. So that's going to be 1. And then again, I have kind of this rectangle thing down here. Its base is 2. The height is 1. So base times height is going to be 2 here. We kind of try to get rid of this little 2. I got rid of too much. And then the triangle up above, again, is going to be area 1. 1/2 base times height. Remember, my base is actually 2. So you do have to be careful about the units here. And so all together, I went, let's see, in the first 4 seconds, from 0 to 4, I went distance 5. And then from time 4 to 8, 4 to 9, it looks like I went -5. And then from 9 to 12, those last 3 seconds, it looks like I went another 4. Remember, this is all area here, so we were multiplying things together. Those units were, let's see, seconds and feet per second. So if I multiplied those two units together, the seconds and per seconds would cancel out, and all I would have is feet. So at the end of the day, I was 4 feet from where I started. Okay. But again, I went in the forward direction for a while, and then I turned around and went in the negative direction, and then I turned around again and went in the forward direction, right? So the next question is, how far did Ryan travel during those 10 seconds, right? And so in that case, you want to count all of this positively. So this is going to be the definite integral of the absolute value of velocity. And so I count that first 5 positive, Instead of negative 5, I again count it positively because although I was going in the negative direction, I was still traveling distance. And then over here again, positive 4. So I kind of keep it all positive, and so altogether this is 14 feet. So I was displaced by 4 feet, but that's because I went 5 feet forward, 5 feet back, and then another 4 feet forward, right? So my total distance is actually quite a bit more. Okay, so in general, if you want a kind of strategy for evaluating out total area, this is a technique that works. So total area under R of t, let's suppose you actually have to show some work, right? If we have our calculators, this is a great way to verify our work, but often you need to show work. So the first step is to figure out wherever it crosses, right? And this is, wherever it crosses, this is where R of t is equal to 0. Notice that I kind of broke this up into 3 sections, and those 3 sections were exactly where it crosses, because this is where I'm going in the positive direction, and then I travel in the negative direction, and then I travel in the positive direction. So figure out when it's 0, because that's going to help me figure out, right, when it crosses. Then use these to break up the interval, A to B, into some pieces, right? So then I was considering not only, the entire interval from 0 to 12, the entire 12 seconds, but I started thinking about 0 to 4, then 4 to 9, and then 9 to 12, right? I broke it up into pieces. And then finally, calculate the area under the curve. Whoops, I guess the curve. On each piece and make it positive. So that's what I did here in this last step, right? I calculated 5, 5, 4. Technically that second one was negative 5, but I just made it positive. I was like, I'm going to count this as positive 5. Add them all together, and that's a way that we can actually find total area. Okay. And again, we've seen a couple of times how this can be useful as far as distance goes, but the claim is there are other applications. So here we are, coffee example, between 9 and 9:20 a.m., at least in the math department, coffee goes very quickly, right? So coffee is added and removed to our air pot here. It's added and removed at this rate of 0.1 t to the fourth minus 3.2 t cubed plus 28.5 t squared minus 59.4 t, and this is in milliliters per minute, where t is the number of minutes after 9 a.m. So, right, sometimes maybe people are taking out coffee, putting it in their cup. Other times, once it gets close to empty, you start refilling it, right? So sometimes coffee's being added, sometimes coffee's being taken away. And so you could ask about how much did the coffee level change between those 20 minutes, but maybe a more interesting question is what is the total amount of coffee that has actually passed through the air pot at this time, right? So, okay, this is talking definitely about a total area, right? Stuff being added, stuff being taken away, all that good stuff. So let's calculate this out. All right, and so I already have this plotted for us. The claim is you can plug this into your calculator. You need to zoom out a little bit, but this is what it looks like right here. So 0.1 x to the fourth, right? This only understands x's, so I had to use x's. Minus 3.2x cubed plus 28.5 x squared minus 59.4 x. And again, this is in milliliters per minute. And so this is the graph that it makes here. If I zoom out a little bit more, you can kind of see we're interested between 0 and 20. It dips down first, and then it comes up, and then it dips down more, and then it comes up more, right? So coffee's being added and taken away and added and stuff like this, back and forth a little bit. And so if we're following that technique, we'd like to figure out when this thing equals 0, right? So if I come down here, it looks like it's 0 at 3, it looks like it's 0 at 11, and it looks like it's 0 at 18. So those are the times, this is how we're going to break up our interval, right? So let's go ahead back to our notes. So when I want to calculate out the definite integral from 0 to 20, the first 20 minutes of the absolute value, right, because we're doing total area, ET, I'm going to break it up, and I'm going to consider first from 0 to 3, and calculate out this dt, then from 3 to, what was it again? 3 to 11. And remember, I'm just going to add up all this area and then count it positively. So in fact, this is slightly different than this right here. I don't need the absolute values inside here. So I'm going to count it positively at the end of it. There we go. Then I'm going to consider the interval from 11 to 18. Add all that up, then count it positively. And then finally the interval from 18 to 20. So I break it up into pieces. 18 to 20. And then count it positively. Okay, so let's go ahead and do that with our regular old calculator. It's pretty good at these things. So I'm going to go ahead into math. 9 is my fint. And I'm going to go ahead and plug in this function here. So 0.1 times x to the 4th power, and then minus 3.2 times x cubed plus 28.5 times x squared minus 59.4 times x. Integrate with respect to x. And the first one, I want to go from 0 to 3. Hit enter. And so it looks like 70 milliliters, and then some, was taken out of this thing. So this is going to be, count it positively, so negative 70.74. And remember, our units here are going to be milliliters, because again, we multiply together milliliters per minute times number of minutes, right? So this is from minutes 0 to 3. Okay, oops, I forgot counting it positively. So I'm going to do positive. And then there's this nifty trick that you can do with your calculators. There's this entry button. So if I do second and enter, it brings up the previous entry. And this means that I don't have to type in the function every single time, right? I can just go now change my interval from 3 to 11. Close parentheses, hit enter. Thanks for a second. So at this point, 629 milliliters were added. 629.76. So 629.76 milliliters were added. And then from 11 to 18, again, go back to this, do second and enter to get entry. And now we're going from 11 to 18, close parentheses and hit enter. So then some was taken out. Ooh, almost a full liter, right? 967 milliliters, 0.26. 67.26 milliliters. And then finally, from 18 to 20, so 528.24, 528.24 were added. Okay, so altogether during this time, how much coffee went in and out and in and out, right? So we can add these all up. 70.74 plus 629.76 plus 967.26 plus 528.24, hit enter. So 2,196 milliliters. 2,196 milliliters went in and out. That's how much coffee went in and out of this thing from 9 to 9:20 a.m. Okay? And of course, we can go ahead and double check. Let's see if I can do this one more time here. Hit the, let's do entry one more time, see if I can back up. And let's go all the way back up here, and I would like to insert. Second delete is insert, and I would like to do the absolute value function. Absolute value function, this is a nice way to check. So I'm doing the absolute value of our previous function. Again, I need to insert a closed parentheses then to stop the absolute value. And now at this point, let's go all the way from 0 to 20, and then close our parentheses. And if I hit enter now, remember we're counting it all positively, and fingers crossed, we're looking for 2,196. Maybe I did a little bit of rounding, but should be pretty close to this. Ooh, it's a tough one for our calculator. I wonder what would become of this video if it didn't end up giving me the same answer. Well, I don't know, guys. I may have broken this calculator or the simulation calculator. Oh, there it is. 2,195.99999. All right, so very, very close to 2,196. All right, excellent. So we were able to check our work just by looking at, calculating across the entire interval, 0 to 20, using the absolute value function here. All right, so the main thing here is that when you see total amount, or total distance traveled, or things like this total, you have to recognize that it's different than just the definite integral. It's different than the net area. Total area is different, and so we need to count this especially. It takes a little bit more. Okay, well, that's it for this video, and that's it for Chapter 6. I'll see you guys later.